Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Okay, let's start today's lecture. And first of all, do you have any questions about previous lectures? About lecture notes, assignments, tutorials? Nothing? Okay. So in the previous lecture, basically we are talking about the inferential tools and the variable selection for generalized linear model. So what I need to emphasize here is that these inferential tools can be used for the logistic regression model we have already talked about, for the binary response variable, and also all the inferential tools and the variable selection methods in this topic can be applied in the more generalized linear models. So that means we can also use those inferential tools in the later topics. For instance, in topic 12, I think we are going to talk about topic 12. It's about multi-category response regression model. So it's a direct generalization of the two-category response regression, which is our logistic regression model. And also those inferential tools can be applied in the binomial count regression and also Poisson count regression model. So that means those inferential tools are developed very generally in this topic. And in order to explain how can we use those inferential tools and also variable selection in real application, so at the end of the last lecture, I'm talking about now suppose we want to develop some artificial intelligence system to automatically distinguish the condition for the weight kernel. So in this topic, we are going to have two conditions for weight kernel. The first one is healthy, and the second one is not healthy. So we are going to develop some automatic or artificial intelligence system to help us to distinguish these two. And usually, I think if you know some knowledge about machine learning or artificial intelligence, so for the logistic regression model is really the first and also the most, I think the easiest one for you to understand for this kind of artificial intelligence. So for example, I think the most famous one is the recommendation system. So for instance, I think you should use some social network site like Facebook. So when Facebook recommends you some friend or something, so actually you can try to use this logistic regression model to recommend friends and also recommending jobs. So for the recommendation system, I think logistic regression model is usually the first thing you can think of to develop this kind of automatic system or artificial intelligence system. So in today's real application, so we are going to use the logistic regression model to predict this healthy or not healthy, or if that's in Facebook, so basically you can predict recommend this friend or not recommend this friend. So if in the job hunting, so that can be recommend this job or not recommend this job. So usually that's the first step for us to develop some artificial intelligence system by using logistic regression model. So our response variable is type 1 in this data set. So you can see if you firstly you can still use similarly use read.csv to read the data set in R. And then if you look at the levels of type 1, so levels function returns the literally the levels of a factor in the data frame. So that means for this type 1, we only have two categories, healthy and not healthy. And in this topic, we focus on predicting type 1. And in the next topic, we are going to talk about type 2, but you do not need to worry about here. So that's in topic 12. So that's our response variable. And also, we have a lot of explanatory variable. So these are our explanatory variables. And notice that there is one explanatory variable which is actually a categorical variable, class. So if we look at the levels of class, we can find that there are two categories. The first one is the hard red winter, and the second one is the soft red winter. So what's the meaning here? So basically, this variable represents two different categories of weight kernels. So two different categories. So we have one categorical variable class, and also we have the other categorical variables. One categorical variable and the other are continuous explanatory variables from density to moisture. So that's the data structure. Any questions about the data? So we want to predict type. So that's what we want to predict. And also we can use this pairwise or scatter plot matrix, if you still remember. We can use this scatter plot matrix to roughly look at those continuous variables. So those are all continuous explanatory variables. So those are continuous variables. So if you still remember the scatter plot matrix, I think in the previous lectures. So usually we can use the scatter plot matrix to roughly look at the visualization of the continuous variables. Here I just want to recall you this so you can have a review of the scatter plot matrix we have mentioned in the earlier lectures. But what I want to say here is that we have this 1, 2, 3, 4, 5 continuous variables. So nothing too much to say. And then we are going to talk about 4 very important slides. So you need to understand these slides. I think these 4 slides are really important. And some tutors may have already talked about it in their tutorials, but I think it's still very important here. And also, you are going to apply these 4 slides in your assignment too, so please be careful about it here. So now let's look at how we use the one categorical variable and also the other 5 continuous variables to predict our response variable. So in order to consider our response variable, so firstly, our response variable is a 2-category response variable with 2 categories. So these are the response variable. So usually the first step is just to consider to use 1 and 0 to represent this response variable. So you can consider healthy be 1 and to be 1 and not healthy to be 0. So in order to do that, we can use the if-else function to help us to do that. But before that, we can, I think I have mentioned it, this attach function. So So after attach weight, so what's the effect of this attach weight? So after we do that, we can use the column name directly, to call a column without using $. So for instance, after we use attach weight, we can use type 1 directly, and type 1 is actually a column in the data frame, if you still remember. So that's the column name. But if you do not use attach weight, you need to use. So if we don't use attach weight, we need $. I think what's the name? The name is weight, I think. We need weight $, type 1. So here we actually need $. To call a column, but if we use attach weight, we do not need to use this $. Anymore. We can just use the column name directly to call a column. So that's the effect of this attach. And the next thing is just to define our response variable. So our response variable y here equals to 1 if type 1 equals to healthy and otherwise 0. So that's our response variable. And also, we need to, because we have already mentioned how can we deal with the categorical explanatory variable, we still try to transform this variable into an indicator variable with 2 values. So this INDSRW is actually the indicator variable. INDSRW equals to 1 if class equals to SRW, and if class equals to HRW, because we only have 2 categories, then this indicator variable equals to 0. And remember that for this 2 category response variable, we can only use 1 indicator variable in our regression model. So that's how we involve this indicator variable in our regression model. And in this case, because we are predicting a binary response, so we consider our GRM function, and also we just involve the response variable and all the explanatory variable, and also we need to specify the family as binomial and the link as the logic, because it's logistic regression model, and binomial just means the distribution is the Bernoulli distribution. I think I have mentioned it here. So because Bernoulli distribution is a special case of the binomial distribution, so what we can do here is just to specify it as the binomial. And the Bernoulli distribution is the model assumption, if you still remember, for logistic regression model. So in this case, we can obtain our logistic regression result in this summary output. So this is the summary output. And then what we can do here is just to look at this table. So firstly, we have the estimate. So estimate is actually the maximum likelihood estimation. And then we have the standard error. So that's something we have talked about. We do not give formula, but we can consider to use them directly in the output. So you can consider it as the standard error, or more accurately, approximate standard error. Remember that in generalized linear model, we can only have this standard error when n is very large of beta j hat. So this standard error can only be obtained when n is large. So what's n? N is the number of the observations. And also we can have the z value. So what's the z value? So z value is the test statistic. So what's the test statistic? It equals to beta j hat divided by the standard error of beta j hat. And it's the test statistic of the test, of the z test. So z test here is h0, which is beta j equal to 0 versus beta j is not equal to 0. So that's the z value. So z value is the test statistic of the z test to test only one coefficient. And then we have the corresponding p-value. So based on this, we can have a look. Firstly, we have the estimation of hardness, the coefficient of hardness. So this is the coefficient of hardness, the estimation of the coefficient of hardness, and it's the corresponding standard error. And also, this z value is just equal to 0.018234 divided by 0.007724. So that's our test statistic. And also we can have the corresponding p-value. And we can find that the p-value is smaller than 0.05. So we can make a conclusion that this coefficient is significantly different from 0. So that's how we can have a look at this table. So any questions so far in this page about how to read this table? Any questions? Okay, then we are going to talk about something important. Please be very careful here. So remember that in the previous case, we have one categorical variable, which is class. And what we do here is just to input an indicator variable here in the regression. So let's try something different. So class is a categorical variable with two categories, right? So R actually can help us to input the class, the categorical variable, directly in the regression. So I haven't mentioned it in my lectures. So that's the categorical X. So R can actually help us input this categorical X into the regression model directly. But in order to understand this output, you actually need to use the indicator variable idea to help you to understand the output. Okay, so firstly, after you input this categorical variable class in the regression, what can you obtain for the R output? So for the R output, you obtain class SRW. Note that you do not get class because class is actually a categorical variable. You cannot get it directly. You actually get something looking like a new class SRW, right? And if you compare this page 31 to the previous page, you will find that you actually obtain exactly the same result. So what's the meaning here? So that means if you input class directly in R, you will automatically generate an indicator variable, which is called class SRW. So what's class SRW? It's actually equal to the indicator variable in the previous page, which is IND SRW. IND SRW, which equals to 1 if the class equals to SRW from the name. So what's the meaning for this SRW? So that means it's actually an indicator variable for SRW. So the other case is HRW. So that's the meaning for this here. That's the meaning when you input a categorical variable directly in R. R actually automatically generates an indicator variable. So you should be very careful here, because when you do that, so what's the meaning here? So that means R automatically generates this indicator variable with HRW as the baseline level. So that's the baseline level. If you still remember what's the meaning for baseline level, so usually baseline level corresponds to the category with the indicator variable being all zeros. So that's the baseline level, and also that's a question, I think, in your assignment 1. So that means this HRW here is our baseline level. So when you input this class variable directly, the first element of this class, levels class, is the baseline level. So you need to be very careful here, and later I will give you a totally different example. Okay, by using one sentence to summarize the result here, so when you input a categorical variable in R directly, so what you will obtain here is that R will automatically generate some one or several indicator variables for this categorical variable. And how to automatically generate those indicator variables? R will treat the first element of this level's output as the baseline level. I think you still need some time to process it because it's actually a very long sentence. So let's look at other examples in order to help you understand it more. So let's look at a totally different case. So now let's consider that. How about we do not consider the previous indicator variable, consider this indicator variable, which is INDHRW. So what's this? So it equals to 1 when class equals to HRW, and 0 when class equals to SRW. So the opposite of the previous one. So the opposite of INDSRW. So if we just input this different indicator variable in our regression model, so what will happen? So this is our output. So if you compare this INDHRW with the previous case, INDSRW, you will see that I think most of the coefficients have the exact same value, but the only difference is that this coefficient has the, compared to the HRW case, it's actually the negative of the coefficient of HRW. So why we have this result? So remember our regression model. If we have, firstly, we have the relationship between these two indicator variables. So what's the relationship? The relationship here is the INDHRW plus INDSRW. INDSRW equals to 1, right? So that's the relationship. So if we have the regression model, generalized linear model G mu y given x equals to beta 0 plus beta INDSRW times INDSRW plus so on and so forth. So that's our regression model. So if we just plug in this kind of relationship between these two indicator variables, beta INDSRW, so that equals to 1 minus IND HRW plus so on and so forth. And then we can obtain, if you rearrange this equation, we'll obtain beta 0 plus beta IND SRW plus, not plus, it's actually minus beta IND SRW times the IND HRW plus so on and so forth. So you can see here, if you rearrange this equation, you will find that the coefficient of the indicator variable of SRW actually equals to the coefficient of the HRW. So that's the reason why we have this negative result compared to the previous case. Because if you still remember when we talk about categorical explanatory variable, I think it doesn't matter for us to use either one of these two indicator variables. So we always have the equivalent model, but the only difference here is that we have slightly different coefficients. So that's how if we use a different indicator variable in this model. But how can we realize that by directly inputting the categorical explanatory variable in R? So what we need to do here is just to change the order in the categorical variable. If you still remember, the first element here is treated as the baseline level automatically in R. So what we need to do is just to change this order such that we have a different baseline level. So if you look at this levels class, so you have this kind of order, HRW and SRW. So if you use this factor function, so what you can do here is just to input the class, the categorical variable, and also you change the order of this categorical variable, and then you will have a different order. So why do we need to have a different order? Because now here we need to change the baseline level. So now the baseline level becomes the SRW. So that becomes the baseline level. The baseline level is always at the first element of this levels function output. So now if you just put this new order class variable in the regression, and then you will obtain this class new order HRW. So what's the meaning here? So that just means it's actually an indicator variable class, new order HRW. It's actually equals to the previous IND HRW we have defined earlier, equals to 1 and 0 if we have the class as the HRW, otherwise SRW. So R automatically transformed this new order class variable into this categorical, into this indicator variable with the baseline level as the SRW. So that's the baseline level. So it's exactly the first argument, first element of the output of this levels function. So I think you still need some time to process it. I think if you first see it, but it's actually not that hard. So by using one sentence here is that you can actually input the categorical variable in R, but R will automatically transform this categorical variable into an indicator variable with something as the baseline level. The baseline level can be found at the first element of this levels function. So I think these 4 slides are a little bit confusing, but are really important. So I will assign a question in the assignment 2 to help you understand it. But from my experience, what you need to do here is just to compare the different methods to define indicator variables and inputting the categorical variable directly. Basically compare these 4 slides, and then you will obtain the conclusion for how to use that in R. Any questions? Any questions about these 4 slides? Okay, now let's just look at the other output from the summary output. So let's firstly look at this testing of overall significance. So in this case, we are testing all the coefficients except for the intercept are zeros. So what we can do here is just to use our drop-in deviance test. So in order to develop this drop-in deviance test, we actually need to define the reduced model and also the full model. So here, our full model is this model logit 4, the last one. So that's our full model with all the variables. Full model with all the variables. And because we are testing all the coefficients except for intercept, so the reduced model is the model with only the intercept. And then the next step for this drop-in deviance test is just to compare these two, the results of these two, so basically the deviance of these two, and then we consider to use the chi-square distribution to compare the test statistic. So we need to specify test as chi-square distribution. And I think the difference between this chi-square drop-in deviance test and also the f-test is exactly here. So we need to change the argument into this chi-square. So that's the only difference. And then we can obtain the deviance of the full model. So that should be the deviance of the reduced model, and that is the deviance of the full model. And this is our test statistic. So our test statistic is actually the difference. So it just equals to this 355.79 minus 241.23. So that's our test statistic. And we need to compare it to the chi-square distribution with the number of the freedom. So what is our number of the freedom here? So we need to compare it to the chi-square distribution with the number of the freedom as the number of the coefficients being tested. So how many coefficients we are testing here? So you need to count, because compared to the reduced model only has the one coefficient, which is the intercept. So we are testing 1, 2, 3, 4, 5, 6. We are testing 6 variables. So we need to compare it to the chi-square distribution with the number of the degree of freedom, 6. And then we can compute the p-value. Here, the p-value is smaller than 0.05, so we can make a conclusion that at least one of these variables are needed in the model. So that's how we apply this overall significance test by using this ANOVA function. But what you can notice here is that if you have a look, so we have 2 deviances, right? The deviance of the reduced model. So this is the deviance of the reduced model with only intercept. And if we compare this page to the previous page, we can also see these 2 deviances. So firstly, we have the residual deviance in this summary output, so which is actually the deviance of the full model in the next page. And also here we have the non-deviance, which is actually the deviance of the reduced model with intercept only. So you can compare the output here. So these outputs are exactly the same as page 35. So that means actually in the summary output, we can use these 2 deviances to construct the drop-in deviance test. So the test statistic should be equal to 355.79 minus 241.23. And what you can do here is just to compare this test statistic to the chi-square distribution. So what's the chi-square distribution? So the chi-square distribution here is the chi-square distribution with the number of the degree of freedom being the number of the coefficients being tested. So here we have, if you still remember, 1, 2, 3, 4, 5, 6, right? And another way to compute the number of the degree of freedom is just to use this 2. So it just equals to 274 minus 268. So that's exactly equal to the chi-square distribution with the number of the degree of freedom 6. So that's how we apply the summary output to help us to achieve the overall significance test. And also, alternatively, you can use this ANOVA function, which is more directly, but which can also help us to understand some output in the summary. Any questions about the dropping deviance test, the overall significance dropping deviance test, a special case? Okay, let's look at another special case of the dropping deviance test. So we can consider to test only one coefficient, even though we can, so for this kind of test, we can consider Z test and also we can consider chi-square test. So we can consider both. So we have already mentioned the Z test result, and we will compare the result of the Z test to this chi-square test. So let's see the difference. So here, in order to test this result, we still need to define the reduced model and also the full model. So for the reduced model, so because we consider this null hypothesis with the coefficient of hardness being 0, so the reduced model is the model without this variable. So the reduced model here is the model without hardness. And the next thing we need to do here is just to compare the difference between the reduced model and also the full model. And still we have the two deviances and also the difference and also the corresponding p-value. So here, because the p-value is smaller than 0.05, so that just means that this hardness is actually, the coefficient of hardness is significantly different from 0, and increase in this hardness can be associated with the increase in the probability that the wedge kernel is healthy. So that's actually from the interpretation. So what's the interpretation here? So if you still remember our model, so our model is the generalized linear model, so which is the G mu given y given x, which equals to the beta 0 plus beta hardness times hardness plus so on and so forth. So that's our model. And if you remember another form of it, another form here is actually the odds. So another interpretation of this model is just to use odds. Odds that y equals to 1. This odds just equals to the exponential of beta 0 plus beta hardness and times the hardness plus so on and so forth. So if we increase, so here, because this coefficient is positive, right? So if we increase the hardness, so we're going to increase the odds of y equals to 1. So that means the odds that the kernel is healthy, because y equals to 1 is equivalent to healthy. And if we increase the odds, so that means we increase the probability. So that's a little bit about the interpretation, and I think I will explain it more. But before that, let's compare the results of this chi-square. This is the chi-square test. So let's look at this, compare this result to the z-test. So what's our z-test result? So this is the z-test result. You can see by using the z-test, we can also obtain this conclusion. The coefficient of hardness is significantly different from 0, but the p-value is slightly different from the p-value for the chi-square. So the z-test result is on page 34. So this is on page 34. So we have a slightly different p-value, but we have the same conclusion to reject the null hypothesis and obtain that the coefficient is significantly different from 0. So I have already mentioned that it's exactly the case for the generalized linear model. We do not have the exact p-values for these two tests, but we have the similar p-values because of the approximation when the sample size n is really large. So everything I have talked about here, including the ANOVA, including this z-test here, so we can only use them when n is large. So when n is small, those are no longer working, and we are going to talk about bootstrap method to solve the problem. But for now, let's only consider the case for n is large, the case when n is very large. So because we have two different approximation results, we can use the z-test or chi-square test to obtain the approximately obtain these p-values. So in that case, we are going to have a slightly different p-values, but we should have basically the same result for the test because we are actually testing the same thing. So that's another special case of the chi-square test. Any questions? So we have the similar p-values, but not exactly the p-values. So what's your question?
When can we consider that n is large?
That's a very good question. I mentioned that a little bit, so I will repeat the question. So the question here that when, in what kind of case n is large? So I think from my experience, I think I mentioned a little bit in my previous lecture. So here, we usually consider this when n is larger than 30 and 50, or in this case, we can consider n is large, but it's purely from my experience. Sometimes it depends on the data set, but I think 30 and 50 may be recognized, I think, by my colleagues. So in that case, I think in this course, just consider 30 or 50. So if n is smaller than 30 or 50, I'm going to talk about the bootstrap method to solve this problem. So if n is smaller than 30, so maybe we need to consider bootstrap method. More questions? Very good question. So that's another case for the chi-square test, to compare the chi-square test and also the z-test. So when you learn this part, I think I have mentioned it, you can consider to compare it to the t-test and f-test, and I think the ideas are very similar. So let's look at the other part. So let's look at how to obtain the confidence interval in this case. So in the summary output, I have already mentioned about the estimation, the MLE here. So if we have a look at still look at the hardness case, we have the MLE, and also we have the standard error, and also we have the Z value. So that value is the MLE divided by the standard error. And also we can use the MLE and also the standard error to compute the confidence interval for the coefficient of hardness. So how can we do that? So basically the MLE here is 0.018 and this standard error is 0.0077. So remember these two values and then we are going to compute. So there is another way here to call these two values. So if you still remember these two values, so this is actually the MLE of beta coefficient of hardness. So that's actually the standard error, approximate standard error. So another way to call these two values directly by using R here is that firstly define the summary output by using this object which is called summary result. So that's exactly our summary output. And in order to call the MLE, so what you need to do here is just to call these coefficients 4 and 1. So what's the meaning for 1 here? So that means the first column. So the first column, so what's the first column? So you need to look at this table. So this is the first column, right? And the hardness, the MLE of hardness is at the fourth row. If you count 1, 2, 3, 4, 1, 2, 3, 4, and also the first column. So this is exactly the maximum likelihood estimation. And also the standard error is actually at still the fourth row, 1, 2, 3, 4, and also the second column. So what you can do here is just to use this summary result, the fourth row and the second column to call the standard error. So in that case, you can just call these two values in the summary table directly without inputting it by hand. And the next thing is just to obtain the confidence interval for the coefficient of hardness. So if you still remember, so the confidence interval here is beta MLE minus plus the quantile Z alpha divided by 2 times the standard error. So we have the MLE, so this is the beta J hat, and this is the standard error. And what we need to do here is just to obtain this quantile. So that's how we can obtain a quantile in R. It's usually if we consider alpha equals to, we consider the 95%, so that means 0.95 equals to 1 minus alpha, and alpha equals to 0.05. So in this case, we need to obtain the 97.5% quantile of the standard normal distribution. So that's how we obtain a quantile in R. So that's exactly the confidence interval by using our formula. And also, I think you can use a function, I think, which is called, which starts from C, I think CON something. I think it's actually in our assignment solution. So you can, alternatively, you can use that function to obtain the confidence interval, and I will not talk about it. And you can have a look at the solution of the assignment 1, and the solution is already uploaded on Wattle, so you can have a look at it. But if we only have the summary output table, so what I suggest you here is that if we only have this table, so what we can do is just to use the formula directly, which is also not that difficult. And also, if you still remember the model, the logistic regression model, I have already written here. So the model here is that the odds that y equals to 1 equals to the exponential of beta 1 plus beta hardness times hardness plus other variables. So that means if hardness is increased by 1 unit, in this case, the odds that y equals to 1 will change by a multiplicative factor of exponential of beta hardness. So that means exponential of hardness actually has some meaning. The meaning here is that exactly the interpretation of this logistic regression model. So that's the interpretation of this logistic regression model. So sometimes we are also interested in calculating the confidence interval for the exponential of beta hardness instead of the hardness. So this is the confidence interval for hardness, for beta hardness. So now we are interested in computing the confidence interval for the function of hardness, for exponential of hardness. It's actually not hard. So what we can do here is just to exponential the confidence of interval of beta hardness directly and obtain the confidence interval of exponential of beta hardness. So in that case, we can have the conclusion that we have 95% confidence that the exponential of beta hardness lies in this 1.0031 and 1.033937. So that's the 95% confidence interval of exponential of beta hardness. So the only difference here is this we just exponential those confidence intervals directly and obtain the confidence interval of exponential. Any questions for the confidence interval? So we do have something new, even though a lot of things are the review material for you. No questions? So let's just take a 10 minutes break and we will continue to talk about more applications. A lot of applications in this topic actually. Okay, let's start the second part of today's lecture. So firstly, any questions? So I understand that in today's lectures, we actually have a lot of details in the interpretation of our outputs and also our codes, especially for the 4 slides. Those 4 slides are really important to distinguish inputting a categorical variable and an indicator variable in R. Any questions for that? So I think I have one question from the student. So here, we try to explain why when we input different indicator variables, we are going to have the negative result. And because for this class variable, for this categorical variable, we can have 2 indicator variables, and these two indicator variables have this relationship. So the summation of these 2 indicator variables are equal to 1. So in this case, if we have the model for one indicator variable, so this is the you can consider it as the model. So firstly, we may have the model for SRW for one indicator variable, and we want to use this model to derive the model for the other variable in this case. So what we can do here is just to input this relationship. We just plug in the relationship here, and then we obtain a new model. So in this case, in this new model, we have a new intercept, obviously. And also, we no longer have the indicator variable of SRW. We have a new indicator variable, which is HRW. So correspondingly, the corresponding coefficient of this variable, we call it the coefficient of HRW. So you can consider it as this model is for the HRW. So we can call beta 0 plus beta IND SRW plus beta IND HRW times the IND HRW. So this is the model form for IND HRW. So that means from the interpretation, the coefficient before the variable IND HRW can be called the beta IND HRW. So if you compare these two, you will find that the coefficient of IND HRW is exactly equal to the minus of the coefficient of the IND SRW. So that's the reason why we have the negative result compared to the result earlier. So we have the same figures, but we have the negative. We have the negative here. This is the positive here, but we have the negative for the other case. For this case. So usually we only need to input one indicator variable, but because sometimes if we have some particular purpose, so we need to input some specific variable to obtain some specific baseline level. But that's something you need to figure out, for instance, in your assignment 2. So that's about these 4 slides. And also, I need to help you to review this binary logistic regression model. So we have our model, a lot of model assumption details, but I think what I can tell you here is that the odds form, so you can consider it as an equivalent form of logistic regression. So you need to understand this form. And it's actually very important in interpretation, and also it's really important. So this form is really important for us to introduce some new models for multi-category response. So here, by using the model assumptions, we actually have this equivalent form. So what's this equivalent form? This equivalent form says the odds that y equals to 1 actually has this exponential of the linear combination of the explanatory variables. So why do we need to use this form? So firstly, it's easier for us to interpret. So in this case, the interpretation of the coefficients in the logistic regression model can be interpreted as the multiplicative factor. So that's from the interpretation. And secondly, in this interpretation, we interpret odds. So what's odds? We use these examples to explain odds is just another way to describe probability. So that means if we increase odds, so that basically means we increase probability. So we actually try to interpret probability, but it's really hard to interpret, so we just change a different way to describe it by using odds. So because we have this equivalent form of logistic regression, I think this is the review in topic 11. So even for me, I still need to review a lot. So if you do not understand some parts, so just look back to review your lecture notes. So that's my suggestion. So in this case, because the exponential of the coefficient here can have this interpretation by using the logistic regression model. So sometimes we are also interested in the confidence interval of the exponential of the coefficient. So that's the purpose in the previous lecture. And also, if you look at the summary output, you can find that there are 3 variables which are not significant: the class, new order, and the size, and also the moisture. So naturally, we are interested in testing whether or not these 3 variables are required. So we can test this null hypothesis. The coefficients of these 3 variables are all equal to 0. So we want to see whether or not at least one of these 3 variables is needed in the model. So because we tested this, so it's the standard, kind of standard chi-square test, dropping deviance test. So what we need to do here is just to obtain the reduced model. So this is the reduced model. So the reduced model here is the model without 3 variables, without these 3 corresponding variables. So that's the reduced model. So what we can do here is just to compare the difference between this model and also the reduced model and the full model, to compare the deviances of these 2 models, and then we can obtain our result. And we can find that by using this chi-square test, we actually have a larger than 0.05 result. So that means none of these 3 variables is needed when the other variables have already considered in the model. So that's from this summary output. So it happens. And also, we can also try different methods to confirm our conclusion. We can try for instance, we can try variable selection method. So in order to try the variable selection method, we still need to use other package. So here, in order to try the sequential variable selection method, we use the package mass. So we need to load this package. And what we can do here is just to use this step AIC function to obtain here, because the direction here is the backward. So we want to obtain the backward elimination by using AIC. So these are the variable selection results. So you can find that here, the other 3 significant variables, the density, hardness, and also weight, are left, but we still have this insignificant variable size by using AIC here. And also, compared to this F-test result, basically we have a different conclusion. So the reason here is that AIC is actually a different standard. So is a different standard compared to F-test. Here it's not F-test, it's actually chi-square test. But the idea is similar to the F-test. Because it's a totally different standard, if you still remember, the testing idea is from the theory of hypothesis testing, but the AIC idea is from balancing the goodness of fit and also the number of the variables. Because it's a totally different standard, so sometimes we have different result. So that's different result. So that's not surprising for us. So please remember that if we have different results, that's not surprising. But in order to see which result is better, we can have a lot of aspects or from a lot of other perspectives to discuss which method is better. So one way is just to consider the forecast. So which method leads to a better forecast? So in the lectures, I will not mention about how to measure the forecast of this binary logistic regression model, but in your assignment 2, I will assign a question to help you understand that if we have the training and also the test data set, so how can we measure the different forecast performance of different methods by using the test data set? So we can here to compare the forecast performance of this one and also this one by using the chi-square test. And also we can try the BIC. So the difference between AIC and also BIC is the weight. So here, the weight of BIC here is log n. So you can see by inputting a larger weight, so this is the weight, is actually the weight for the number of the variables. Because we put a larger weight in BIC, so that means BIC emphasizes the number of the variables more, so it usually selects the model with a smaller number of variables. So you can see it leads to this model with only one variable. So usually that's the case for BIC. Still, in order to compare which one is better, from the forecast point of view, you need to see the forecast performance of the test data set. So that's in your assignment 2. You can compare the results of the AIC and also BIC. And also, I give another one, which is the stepwise AIC. So it gives exactly the same result compared to backward. So it gives the same result. I think it's just this case. Compared to backward. So if you look at the R code here, even if we consider a totally different model, we consider generalized linear model. So it's actually from the GLM output. But the way to apply the R function here to obtain the variable selection result is the same compared to the multiple linear regression model case. So that means by using this similar ideas, we can still accomplish the variable selection even for the generalized linear model. And at last, we detach weight. So after we detach it, so that means we can no longer use the column name directly. We need to use the dollar to call a column. So basically, that's the opposite of attach. So I think that's the end for this lecture. A lot of details in the R output, so please be careful about it. Any questions? So you can try to figure out some questions. So let's take 1 minute break, and then we're going to enter the next topic about multi-category response regression. Okay, let's start this new topic because we have already considered the two-category response regression. So normally we should consider the multi-category response regression because it's a direct generalization. So that's another way to consider a different generalized linear model. But I just do not understand that. Maybe this is the only chance for you to learn this multi-category response regression model in this university. And I do not understand why in the generalized linear model course there is no this part. But still, I just want to introduce it. It's a direct generalization, and it's actually not that difficult. So in order to talk about this topic, so firstly, I need to introduce, so what's the multi-category response variables? So you may think it's not that hard in the beginning, but actually you need some time to process the difference between the multi-category and also the two-category. So the most important difference here is the order, and I will explain more details. So if we consider this multi-category response regression, so we may have two kinds of regression models. The first one is the nominal response regression, and the second one is the ordinal response regression. So from the name, the difference is actually from the order. So I will explain the difference. So you can always look at some references. So firstly, in order to explain the difference between the multi-category and also the two-category, so let's look at these three examples. So the first example is the example with two categories. So imagine that you are a customer and you want to buy a car. So you care about the color of your car. So here we have two values. First one is red and the second one is yellow. So that's the typical case for the binary variables. And the example 2 here is that actually we have more color for your car. We have red, yellow, and blue. So here we have three categories. So in this case, we can consider this multi-category response variables with three categories. And example 3 here, we actually consider this kind of variables which can appear in a questionnaire. So I think you, in the university, you should receive a lot of questionnaire from emails and from a lot of different forms. So here, consider this categorical variable with three categories: disagree, neutral, and agree. So let's just look at these three examples in details. So for the first example, I think you have already seen it. It only has two categories. So what we can do here is just to consider the indicator variable to represent this two-category response variable. So we can consider to use one to represent red, 0 represent yellow, or you can consider to use 1 to represent yellow and 0 to represent red. So it doesn't matter. And for the second case, we usually call nominal response. So that is actually the three-category variable with three categories: red, yellow, and blue. And also, example 1 can also be called nominal response, but with only two categories. So the example 2 is the direct extension of example 1. So the last one is a little bit different. We call it ordinal response because clearly disagree is smaller than neutral and neutral is smaller than agree. So we have this kind of order for the third example. So we call it ordinal response. So you can see, because we have this kind of order here, usually in questionnaire, we can consider to set 1 equals to disagree, 2 equals to neutral, and 3 equals to agree, right? So that's the usual way to design a questionnaire. But the problem here is that you need to be careful because when you set 1, 2, 3, so usually we have 2 minus 1 equals to 3 minus 2, 2, right? So that's because 1, 2, 3 actually have numerical value, numerical meaning. But the problem for the neutral disagree and agree here is that we do not have this relationship. So that means, remember that even though we use 1, 2, 3, but we do not have the numerical meaning for these 3 categories, for this kind of ordinal response. We do not have the numerical meanings for different categories. So that's the very important feature for this ordinal response, no numerical meaning. But later we are going to talk about something which is called count data, like how many students do we have in this lecture theater? 1 student, 2 students, 3 students. So in this case, we still have the numerical meaning, but for the ordinal response, we do not have the numerical meaning. So for the count data, we are going to talk about it later. So today we focus on this kind of ordinal response without any numerical meaning. And also we can consider the example 2. So if you still example 2, so red, yellow, blue, we do not have any order for these 3 variables. So that's the reason why we call it nominal response. And it doesn't matter for us to set 1 equals to red, 2 equals to yellow, 3 equals to blue, or 2 equals to red, 1 equals to yellow, and 3 equals to blue. It doesn't matter because we do not have the order. So that's the very important difference between example 2 and example 3. Because we have different kind of situations for example 2 and example 3, so we have 2 different models. You can consider them as the 2 parallel models for the multi-category response. One is called nominal response regression, and the other is called ordinal response regression. So that's basically the beginning. So actually, that's the most important part in today's course. So if you can understand the difference between the nominal and ordinal, so you can select the correct model, and then you can use the model to fit the data appropriately. So that's usually the first step, and usually the most important step. And one thing I need to remark here is just to talk about some relationship between the ordinal response and the nominal response. So actually, ordinal response is a special case of the nominal response, obviously, because the only difference between the ordinal response and the nominal response here is that ordinal response has an order. So that's the only difference. So in this case, because ordinal is a special case of nominal, so the nominal model can be used for the ordinal response. But the problem is that the ordinal response has more information, so that the more information is the order. So if we neglect the order but use the nominal response regression model for this ordinal response, so usually we lose some accuracy, because when we apply this nominal response regression model, we do not consider the order. So basically, if we do that, we do not consider the order. We do not consider order. So in that case, that will lose some model efficiency, not model efficiency, model accuracy. So we will show that in the real examples, and in that case, you can understand it more clearly. And also that just introduces our overview of this course. So we have already talked about continuous 2-category response Y by using the multiple linear regression model and the logistic regression model. So in today's lecture, I'm just talk about the multi-category response Y by considering nominal and ordinal response regression model. And in this case, we may have continuous X and categorical X. So when we have the categorical X, we always use the indicator variables to help us. Even if I have mentioned, I think in the previous lecture, that you can input the categorical variable in R directly, but R actually automatically transforms those categorical variables into the indicator variables for us. So still, we still consider the indicator variables actually in R. So let's look at the first one, the nominal response regression model. So in order to talk about this model, so let's look at the review part, if you still remember. The equivalent form, or the equivalent expression for the logistic regression model by using odds. So this is the equivalent form. So that's the odds that y equals to 1. So in other words, you can use the pi x as the probability that y equals to 1, and in this case, we are going to have this equation, right? So that's the, you can consider it as the form of another form or an equivalent form of the logistic regression model. So here we have this probability. So that means actually for the logistic regression model, we model the probability. So in order to generalize this model, we should still consider to model the probability for the multi-category response regression model. So that's the idea. Because for the logistic regression model, we model probability. And so similarly, in the multi-category response regression model, we should also model the probability. But how can we model it? So that's the question. So in order to talk about how to model it. So firstly, let's just simplify the notation a little bit. So because we focus on model probability, so let's just consider that pi is actually some probability without using the x. So that can make the notation more simple in this case. So for the multi-category response case, so we are also interested in modeling the probability. So let's consider that we have categories from 1 to capital C, and the probability of each category can be represented by using the pi c. So pi c is actually the probability that category C happens. So for instance, it can be the probability that you buy a yellow car. So in that case, we are going to have C probabilities, right? Pi 1, pi 2, until pi c. And because it's probability, we should have some equation, because you can only, for instance, you can only select the color from these C categories. So that means the probability, the summation of those probabilities equals to 1, because you can only select one from those probabilities. And the next part is to talk about the baseline level for the response variable. So that's something new. So baseline level category. But this is for the response variable. It's not for the category. It's not for the explanatory variable. So it's totally different from the way when we consider the indicator variables to deal with the categorical explanatory variable case. But here, similarly, we should have some baseline level. So in this case, what we do here is just to consider C equals to 1 to be the baseline level, and then we just put the probability of this baseline level as the denominator in the model. And what we do here is just to consider the model of the probability of C divided by the probability of the baseline level. So what's the meaning here? So basically, you can consider pi 2 divided by pi 1 equals to the exponential of beta 2, 0 plus beta 2, 1, x1 plus so on and so forth plus beta 2, k, xk. So that's the model for beta 2 divided by, for pi 2 divided by pi 1. Also, we can consider pi 3 divided by pi 1, and so on and so forth until we have the pi capital C divided by pi 1. So that means we are going to have the C minus 1 equations to describe this model. So that's the difficult part. So we have a lot of equations to describe a model, not using only one equation. And also we have totally different coefficients. You can see those coefficients depends on C. For instance, the coefficients here for pi 2 divided by pi 1 here are actually dependent on 2. So we have 2k. So that means if we have the model for pi 3 divided by pi 1, so we'll have totally different coefficients. So that's the difference between the nominal response regression and also the classical binary model. But because binary is actually a special case of the is actually a special case for the nominal response. So you can have a look. So what's the binary model? So you can actually write this binary model here. So the binary model here is the probability of y equals to 1 divided by 1 minus probability y equals to 1 equals to exponential of beta 0 plus beta 1 x1 plus beta k. We still have the variables in the middle, beta k, xk. And what's the probability of y equals to 1? So that's basically the probability of y equals to 1. So just write it here. But 1 minus probability of y equals to 1 here is exactly equal to the probability of y equals to 0, right? So in this case, you can actually write it in this way. So that equals to pi 1 divided by pi 0, right? So that's exactly the form of this multi-category or the nominal response regression model. So it's a special case. By considering the 0 case as our baseline level. So in this case, you can directly extend the binary logistic regression model to the nominal response regression model by considering the ratios of probabilities. So that's the direct extension. And also, if we have this model, we can actually write down the likelihood function, and the next step is just to obtain the maximum likelihood estimation. And if we have the maximum likelihood estimation, what we have talked about for the inferential tools and also variable selection can be considered. So any questions about this model? Just extend the ratio here, extend the ratio for the binary into this ratio with more categories. So that's if I use one sentence to describe the model. Any questions for this model? So I think this may be new for you, but do not worry. In the real example, I will rewrite the model and try to interpret this model for you. And one thing I think I have forgotten here is that why we only need to use this c minus 1 equations. So that means we only need to use pi 2 divided by pi 1, pi 3 divided by pi 1 until pi c divided by pi 1. I think the reason is obvious here is that we only need to use this c minus 1 equations. And also we can add one equation, so if you like. So the equation can be pi 1 divided by pi 1 equals to 1, so that's obvious. And also, because we actually have this relationship, you can compute pi 1. So pi 1 plus so on and so forth plus pi c equals to 1. So that means if you have this c minus 1 equations, you can use this extra equation to compute all the values of pi 1 to pi c. So that's totally enough for us because at the end, we are going to use this model to predict the probability of each category. And if we can predict the probability of each category, so to some extent, we can predict the response variable. So that's what we need for this regression model, to use this regression model to predict some specific category in this case. For instance, we may be interested in predicting which color you are interested for your car. So in this case, by using this model, we can predict the color from red, yellow, or blue. So that's this model, and let's talk about a real example to help you to understand this model better, because this model is new for you. So this example is the same. So what's the difference here is that we further classify the not healthy category into two categories. The first one is the partly diseased, and the second one is the diseased. So in that case, we have more information on the category not healthy. And because now, in total, we have 3 categories, so we are going to consider the multi-category response regression model instead of the binary logistic regression model. So that's the difference between this real data and the data, I think, in the previous topic. So here, we are going to predict type 2, so that's our response in this topic. And the only difference here is that in the previous topic, we only consider not healthy, but in the this example, we consider not healthy can be split into 2 parts. The first one is diseased, and the second one is partly diseased. So we have these 3 categories. And in order to use the nominal response, so obviously we have the 3 categories, right? We have the multi-categories. So straightforwardly speaking, because we have already talked about the nominal response regression, so let's try to use the nominal response regression model to fit this 3 category response variable. So this is the variable with 3 categories. And what we can do here is just to use the package, which is called NNNet. So in order to use this package, you need to install it first. So after you install it, you do not need to install it again, so just load this package. And the next step is just to input the response and also explanatory variable. I think that's standard, I think, in R. So in this case, we are not going to use the GLM function. We are using the multi-norm function. So that's the multi-category nominal response regression model function. You can consider in this way. And the type 2 is the response variable. And also we have the other explanatory variables. And we have the data set. So we are using the same data set but different response variable. And here you can see we input a categorical X here. So we actually have a categorical X here directly in R. So what's the meaning here? So if you still remember those 4 important slides, so that means R will transform this variable automatically into an indicator variable. So I will explain this indicator variable. So that's the model fitting. And in order to have a look at it, we are going to use the summary to obtain our model output. So that's our model output. So a lot of figures, so how can we understand it? So I will try my best to help you understand it. So firstly, let's just try to look at this one. So we have the categorical X. But in R helps us transform it automatically into an indicator variable. So this indicator variable is called class RW. So that is the indicator variable of 1 and 0. And if we have the SRW, so we have 1, and HRW, we have 0. So that's the first thing I need to explain to you. So that's the variable. And secondly, in order to make everything easier, so let's just try to rename it. So firstly, rename the class SRW as X1, X2, and then density as X2, X3, X4, X5, X6. So that can make everything easier. And also we have our response variable as Y. So Y has 3 categories. So what's the 3 categories? These are the 3 categories. So in order to make everything easier, so let's just try to define these 3 categories as 1, 2, 3. So Y equals to 1, 2, 3. So that means if we have these orders by using this levels function, so the first one is defined as 1. So that means the first one is the baseline level category for the response variable. So that's the baseline level. So if you just review the 4 important slides I have mentioned today, you will find that we always have the first one as the baseline level, no matter for the explanatory variable or for the response variable. So if we have the first one as the baseline level, so what's the meaning here? So that just means that we consider the diseased one as the baseline level, and the model can be written in this way. So because we have 2 categories, so C equals to 1, 2, 3, and our model can be written as pi2 divided by pi1 equals to beta 2, 0 plus beta 2, 1, x1 plus so on and so forth plus beta 2, 6, x6. So that's our first equation. And the second equation is pi3 divided by pi1. And that equals to beta 3, 0 plus beta 3, 1, x1 plus so on and so forth plus beta 3, 6, x6. So we are going to have 2 equations to describe this model. So that's the difficult part for this multi-category response model. Because we have 2 equations, so we have totally different coefficients, right? So in that case, we can use the maximum likelihood estimation to obtain the coefficients. And here, remember that what's healthy? So healthy is represented by using 2. So that's 2. And partly diseased is actually 3. So this model can be represented here by using those estimated coefficients. So the intercept here is actually the estimation of beta 2, 0. So you need to look at these equations and compare these equations to those coefficients. So here, this intercept here is the estimation beta 2, 0 hat. And also we have the beta 3, 0 hat here. And let's just denote another one. So this is the beta 2, 6 hat, and this is the beta 3, 6 hat. So that's the how to look at this table. So the coefficients part gives the exact maximum likelihood estimation for the coefficients. But in order to understand the coefficients, you actually need to write down the meaning of this healthy and partly diseased, how we use that, and also what's the meaning for the model in order to understand the meaning of those coefficients. And you can find that here in total we have, you can count, in total we have 14 coefficients. Because we have 2 equations, in each equation we have 7 coefficients. And correspondingly, we have the standard error. So this is the standard error for those coefficients. And these standard errors are also the approximate standard error. For instance, we have the beta JC, maybe beta CJ, the corresponding coefficients. So if we have the standard error and also we have the estimation, if I ask you to compute the confidence interval for some coefficient, I think that's straightforward. Just to use the estimation minus plus the quantile times the standard error. So that's the corresponding standard error, and that's how we look at this summary table. Any questions for that? I think the only difficulty here is that we have more equations, so that means we have a lot of coefficients.
If we do 2 logistic regression for the models separately, would I get the same answer?
Very good question. So the question asks if we consider the logistic regression model, do we have the same result for these coefficients? And the answer is no. And remember that here in this logistic regression model, the pi1 plus pi0 is always the summation of pi 1 plus pi 0 equals to 1, right? So that means we only have 2 categories. So if you consider to use the logistic regression model, for instance, you just try to separate these 2 equations and try logistic regression directly for these 2 equations. The problem here is that pi 2 plus pi 1 is not equal to 1 because we have another category which is pi 3. So that's the difference between the logistic regression model and this nominal response regression model. So my suggestion here is just to consider if you have more than 2 categories, just consider this model directly, and I think that's more straightforward. More questions? Thanks for the question. Residual deviance, that's a very good question. So we do not talk about the, if you still remember, topic 11. So we talk about how to derive the likelihood, and then we talk about how to define the deviance, right? So the deviance, so what's the definition for the deviance? So let's just have a quick look at it. Dropping deviance hypothesis testing. So this is the definition for the deviance, right? So deviance equals to 2 times the log likelihood value. So if we can write down the likelihood, and also we try to derive the likelihood for the binary logistic regression model. So similarly, here we can try to derive the likelihood for the nominal response regression model, but it's actually more involved. So in that case, I do not mention it here, but you can derive the log likelihood value. And if you can derive the log likelihood value, so you can compute the deviance. And if you can compute the deviance, you can compare the output for the logistic regression model, if you still remember. So the R output here is here. For the binary logistic regression model, we have the residual deviance, right? So this residual deviance here is actually the deviance of the full model. It's the deviance, basically the deviance of the model here with all the variables. So deviance of the model here. So similarly, in this R output, so we are going to have the residual deviance. So it's exactly the deviance of the model. So this is our model.